Plane has this vector equation, and we're asked to find the perpendicular distance from a point to the plane. So I could represent it like this. And the perpendicular distance is actually the shortest distance to the plane. Now, this question kind of looks complicated until you remember there's literally a formula in the formula book that tells you the perpendicular distance. So this here is our alpha, beta, gamma. And then this is our equation. Just take the dot product. We're going to get, remember this is x, y, z dotted with 3 minus 4, 2 equals 5. Apply the dot product, we get 3x minus 4y plus 2z equals 5. Just then write it in this form, so it's actually going to be minus 5 equals 0. And we've got our n1, n2, n3. Remember, that's the normal vector here to the plane. Okay, so our distance, just got to sub it in carefully. So the modulus of 3 times 6 minus 4 times 2 plus 2 times 12, and then I'm adding d, which is minus 5, so I'm just minusing 5 here. I'm not going to in this video show you where this formula comes from, but it is worth looking into, and I go through it in other videos. If you look through my vector ones, actually the textbook doesn't derive it, which is a bit frustrating, but I think it's quite a nice exercise to do. And then we're dividing by the square root of 3 squared plus, will it be minus 4 squared? But that's the same as 4 squared plus 2 squared. Okay, and you can basically just put this in your calculator now. So 18 minus 8 plus 24 minus 5. It ends up being the modulus of 29, or just 29. But actually, when you do 3 squared plus 4 squared plus 2 squared, you get root 29. So our answer is itself root 29. Next up, we're given a different plane with a slightly different way of representing it. So what's going on here actually is normally you have another vector that you're adding, but actually the origin is on the plane, because if lambda and mu are equal to 0, which they can be at some point, then you'll get r is 0, 0, 0. So it must be. And this is one direction vector, takes us in a certain direction, and then this is a different direction vector. Okay, I mean, I'm not trying to draw them perpendicular. It could even go in, that way or whatever. But if we take a linear combination of these, we can get anywhere on the surface. Of course, it could be negative and then it would go in the opposite direction. So yeah, if I wanted to get to here, I could just add this bit on and then add that bit on, and there I am. So this question then says, show that this vector here is perpendicular to pi 2, the plane. So what we can do is just show that that vector is perpendicular to both the direction vectors. And if that is the case, then it'll be perpendicular to the plane. So for this, we use the dot product. Minus 1, minus 3, 1, dotted with 2, 1, 5 is equal to minus 2, minus 3 plus 5. It's 0. So therefore, perpendicular. Because remember the dot product, you can also write it as the product of the magnitudes times cos theta. Cos theta has to be 0 in this case, because the magnitudes aren't 0, and theta would be 90 degrees. That's why they're perpendicular, but you can just go straight ahead and state it. And then we'll also do minus 1, minus 3, 1, dotted with 1, minus 1, minus 2. That becomes minus 1 plus 3 minus 2, which is 0. So therefore perpendicular to this as well. So I said, just to finish, running out of space, but I said minus 1, minus 3, 1, perpendicular to both direction vectors. Therefore, minus 1, minus 3, 1, perpendicular to pi 2. A consequence of this is that that vector, minus 1, minus 3, 1, is a normal vector. Has to be. It's perpendicular to the plane. We've just shown it. So we're then asked to show that the acute angle between pi 1 and pi 2 is 52 degrees to the nearest degree. Oh, don't forget, I've earlier worked out this was the equation of pi 1 written kind of in the r dot n formula. I just sort of brought it together. Let me bring that down as well. Okay, so we've got a plane, and then we got like another plane, and we're somehow trying to find the angle between them. But here's the thing. We know that the normal is perpendicular to that plane, and we've got another normal that's perpendicular to the other plane. They're both at right angles to the plane, so the angle between the planes is going to be the same as the angle between the normals. Incredible. So now we can just focus on this and this. Find the angle, and that will be the same as the angle between the planes. It's got to make sure it's acute. If it ends up being obtuse, we'll just do 180 minus. So we're going to look at minus 1, minus 3, 1, dotted with 3, minus 4, 2. And we're going to work it out in two different ways. First of all, the quick way, which is to multiply the components, minus 3 plus 12 plus 2. And then the other way, which is to do the magnitude. So we've got A dotted with B, as well as equaling AX BX plus AY BY plus AZ BZ is the magnitude of A times the magnitude of B times cos theta. So magnitude of A is going to be 1 squared plus 3 squared plus 1 squared, square rooted. Well, that's just root 11. For the next one, we get root 29. And then we times by cos theta. That means cos theta is going to equal 11. And I work out minus 3 plus 12 plus 2 divided by root 11, root 29. Actually, I didn't write down what the decimal was when I did this question. I just went straight ahead and did inverse cos of all of that. And we get 51. You know you've done it right when you get that, 51.983, which to the nearest degree is, of course, 52 degrees. So there we go, a few little aspects of vectors to deal with. Good job.